On the first problem, it was describing a linear regression, but they really didn't have you do the linear regression. They did it all for you. It was another wolves problem by coincidence, and they were trying to associate the weight of the wolf as a function of its length or its size, but they specifically said length. And they gave you the relationship somewhere right here. Okay. And they, in the narrative, they said it was positive and linear and strong, and they just wanted you to define what that meant in the context of this problem. So you can see what I wrote. You know, the fact that it was positive means the two variables trend together. As the wolf increases in length, the weight tends to increase as well, or the other way around. Okay? As the wolves get shorter in length, their weights tend to decrease. So when the two variables are trending in the same direction, it's a positive association. And then linear would simply be, you know, if you saw a scatter plot, you would see that the model forms a line, a trend line. And then strong just means the data points. Again, if you saw a scatter plot, which you didn't, but if you saw a scatter plot, the points would be tightly clustered around the line of best fit. That would make a strong correlation. Okay. Oh, here's where they gave you the actual line of best fit. Now, I rewrote it to actually put in the variables. I like doing that just so I know exactly what I'm talking about. And the weight was in kilograms and the length was in meters. And they asked you to define the slope in the context, obviously in the context of the problem. We've done that, you know, dozens and dozens of times. For each additional 1 meter in length, the wolf is predicted to increase in weight by 35.02 kilograms. And then the last problem was based on residual, okay? But this time they gave you the residual. They said, we know for a fact the wolf is 1.4 meters in length. What is its weight? Okay. If we know for a fact that it has a residual of 9.67. So the starting point in this problem is just understanding they told us the real x, but we are solving for the real y. Okay. So we need to plug in the x of 1.4 into the equation to find the estimated or the predicted value of y. Okay, so the model predicts that the wolf would weigh 32.568 kilograms. Now we go back to the equation for residual. Residual is y minus y hat. So now it's just an algebraic equation that has 3 variables in it, and we know 2 of them. They told us the value of the residual, so I substituted. They didn't tell us, but we could figure out the value of the predicted value of y, the y hat. Okay. So what we're actually solving for is the wolf's real weight, the real y. Okay. So you just, solve for y. And that's it. So 22.898 kilograms. The second problem is all about people who ask for water cups at restaurants, but then they go to the soda dispenser machine and they actually get, a soda with your water cup. I know nobody's done that. They said in a random sample of 80 people who have asked for a water cup, 23 people actually filled that water cup with a soft drink. Okay, so that gives you a P prime right there. This is a proportions problem. Okay, so and the sample proportion is simply 23 out of 80, which is 0.2875. Okay, now this is just information from the problem. That's what I like to do when I read a problem. I like to jot down the pertinent information. Okay? So the A, they want a confidence interval, okay, to represent the population. Okay, so it is a one prop Z int. Okay, just title your work, and you don't have to show any formulas at all. Okay? So you do a one prop Z int. Your calculator is going to ask you for the X and the N, 23 out of 80. Okay, and it's going to ask probably what level do you want to do it at, and we'll put in 0.95, and this is what you get. Okay, and then explain it. We're 95% confident that the true proportion of all customers who ask for a water cup yet fill it with soda is somewhere between 0.188 and 0.387. Okay, now just like a hypothesis test, nowhere in this problem did it say assume the conditions and the assumptions have been met. So we need to do the conditions and the assumptions in order to do this analysis. And here they are right here. Random was given, independent was assumed. Okay. 80% is less than 10% of all customers who ask for water cups. Okay. And then there is the success and failure. What is normally N times P and N times Q, but there is no P and Q in the problem. So it would be N times P prime and N times Q prime. Okay. Basically, it's the results of the survey or the sample. Okay. 23 people did ultimately go and fill up that water cup with soda. Okay. And 57 people didn't. Both of those numbers are greater than or equal to 10. Okay. So we've met all four conditions. Okay. So we're now done with part A. Now in part B, they said, okay, let's say 3,000 customers. Okay. And it costs the place 25 cents per customer who does this. Okay. Well, first thing we got to do is find an interval that converts the proportion to the number of people who actually do it. So in a group of 3,000, the low end would be 564 people, and the high end would be 1,161 people. Okay. Now, each one of those people who do this cost the place 25 cents. Okay. So now we're going to convert the number of people to money. Okay. So the low end of the interval says, hey, it's costing us 141 bucks, and the high end of the interval says $290.25. The third problem is, it basically turns into a tree diagram, but it's a combination of using the Z-chart and a tree diagram. So, the narrative is kind of long. It's about, a store that gets watermelons from farm J, which I think is an organic farm. So they are organic watermelons. Now, the distribution of those melons are normally distributed. Okay, so the minute I saw normally distributed up there, okay, I got to draw a Z chart, okay, with a mean of 133 and a standard deviation of 5 millimeters. And they said, well, what's the probability that a randomly selected watermelon who comes from farm J exceeds 137 millimeters? So we just mark 137 and shade to the right. Don't mark 138 because then you're missing all those numbers in between. Okay, so just mark 137, even though it said more than 137. The more than is simply an indication of shading to the right. Okay, and then just do your normal Z, 137 minus 133 divided by 5. Okay, because it was asking what's the probability that one randomly selected melon. There wasn't a sample. So you don't divide by square root n or anything like that. So it's 4 over 5, which is 0.80. Now remember, that's a z-score. That's not your final answer. That's not the probability. So look on your z-chart at 0.80. I don't have one handy or else I would show you. Oh yeah, here's one. So look up on your z-chart for 0.80 and you get 7881. But we shaded to the right, so it's 1 minus 0.7881, and so the answer is 0.2119. Okay. Now, they also gave you information about watermelons from supplier K, which are non-organic. Okay. The probability that their melons are greater than 137 millimeters is 0.8413. Okay. Now, they didn't say anything about being normally distributed, but ultimately you don't need one. Okay. Because problem B is now perfectly set up for a tree diagram. It said 70% of the melons in the store are from supplier J, whereas 30% are from supplier K. Now, when it comes to the size, 137 seems to be like the important number. From supplier J, the probability that the melon is greater than 137 millimeters is 0.2119. That's what we just found out in the first part of the problem. Now, from supplier K, the probability that any given melon is greater than 137 millimeters is 0.8413. That was simply a given. We didn't have to come up with that at all. That was a given. So the next problem was, to finish off the problem, it just said, okay, you're going to this store and you buy a melon. What's the probability that it's bigger than 137 millimeters? Okay, well, you just add this and this. It might be from supplier J. That's the probability it's from supplier J. That's the probability it's from supplier K. They didn't ask anything about the supplier. So just add these two, and that's your answer. Now, problem C is the conditional. Okay. So this problem is you go to the store, you buy a watermelon. Okay. You know for a fact that it is more than 137 millimeters. Okay, that is a fact. Okay, it's a given. So what's the probability that it came from supplier J? So in notation, this is what it looks like. So this problem is simply an extension of the previous problem. Okay. We know the overall probability of the melon being greater than 137 millimeters, because that was our answer right here. So that's our denominator. Okay. Our numerator is the probability that it came from supplier J. And so that answer is 0.37 0.02. Okay, you talk about a long narrative. Problem number 4, it takes a while to get your head wrapped around what they're talking about in problem number 4. Now, one thing, you're not going to need your calculator at all. It is totally an analysis problem, and it all revolves around how you read or can you read a box and whisker plot. Now, the problem is this. They are analyzing 3 different chemicals, chemical X, chemical Y, and chemical Z, within the clay components of the artifacts at 3 different sites, site 1, site 2, and site 3. Okay, so like I said, it might take a couple seconds just to figure out what this is all about. Okay? Now, with all this information, okay, they focused on chemical Z for question A. As far as chemical Z is concerned, okay, there are similarities and there are differences at each site. Okay? What are some of the similarities and the differences? Here's chemical Z for site 1. Here's chemical Z for site 2. Here's chemical Z for site 3. So you can see what I wrote. Okay? It appears that the medians are really close to being in the same spot. They might even be equal. I don't know, because the scale isn't that precise. Okay? But the medians are similar, okay, at all 3 of the sites. Okay? Now, look at the shape. Okay? At site 1, fairly symmetric, not skewed. Site 2, fairly symmetric, not skewed. Site 3, fairly symmetric, not skewed. So that's what I wrote. All 3 are fairly symmetric. So that's a couple of similarities. Now, okay, what are the differences? Well, again, 1, 2, and 3. The biggest difference I see is in how spread out they are. And in a box and whisker, the size of the spread is an indication of variation. So the variations are different. Okay, site number 2 has the smallest amount of variation, whereas site number 3 has the highest amount of variation. Okay. And I think that would do for A. I mean, they're not asking you to write a book. They're just asking you to come up with a few similarities and differences. Okay. Now, the B. The B question says, based on what is the most likely site where the sum of the percentages add up to 20.5? Well, I'm going to use the median. I mean, that's the best number I can think of to use, and you're going to have to guess. So at site 1, this is a little more than 7. This one looks like it's at 13, so there's 20 already right there. And then this one is back to 7 again, so there's 27. Okay, that doesn't seem right. Okay, site 2 doesn't really seem right either, but if you look at site 3, the median is exactly 6 for chemical X. It's a little bit more than 7 for chemical Y, so I called it 7-ish. And it looks like it's right in the middle, and it looks like it's 7 for chemical Z. So you take a 6 plus a little bit more than 7 plus 7, and there you are. You're a little bit more than 20, okay, which is really close, approximately 20.5, which is what they asked for. All right, and then the last problem, okay, was among the 3 sites, okay, which chemical, if you found a sample of that chemical, which chemical would you be most confident that you could identify the site from which that chemical came from? Okay. And the answer is chemical Y. Okay. Because there's no overlap. Look where chemical Y is in set 1. It's way up here. Look where chemical Y is in set 2. It's way down here. And look where chemical Y is in site 3. There is no overlap in any of those 3 box plots. Okay? So it's very distinct. Okay? If we analyzed chemical Y, whatever result we get, we can be confident of what site it came from. Okay? Because there's no ambiguity, because there's no overlap. Chemical Y is very distinct at each site. Problem number 5 should be a very familiar problem. The first thing you see in problem number 5 is this table, and you're probably thinking maybe some type of a chi-squared problem, and you would be right. The problem is all about investigating the association between the age at which someone is being treated for schizophrenia and their gender. So this is a 2x4 matrix, 2x4, 1, 2, 3, 4, okay, 2x4 matrix. Okay. And notice what they did, okay? They even gave you the segmented bar graphs, okay, broken down according to age, okay? Men is the dark, okay, and women is the diagonally striped. Now, as I'm looking at this, remember, make a picture, make a picture, make a picture, because pictures tell you a lot. I'm already seeing a trend in this data. It seems to be that the older you get, the more likely the person being treated for schizophrenia is a woman and not a man. Okay. So my gut reaction is there does seem to be an association, and that association is exactly what I just said. It appears that the older you get, the more likely the person is a woman. But that's just, observation. We need some numbers to help us out. Okay. So we're going to do a chi-squared test of independence. Okay. And I'm going to use the word association because that was the word used in the problem. You can see the null and the alternative. The null hypothesis says age and gender are not associated because they are independent. The alternative says they are associated. So in the calculator, I'm going to put in my 2x4 numbers in the matrix, and I'm going to do the chi-squared test, and this is what I get. My test statistic and my p-value. Okay. My chart, since it is a 2x4 matrix, 2 minus 1 is 1, 4 minus 1 is 3, 1 times 3 is 3, so there are 3 degrees of freedom in the problem. So I look on my chi-squared chart, the critical point is 7.81. My calculator tells me it's 10.88 is the test statistic, so I'm in the rejection region. Okay. The p-value also tells me to reject because it's less than 0.05. So at 95% confidence, there is evidence to reject HO, okay, in favor of HA. And the analysis actually confirms what we initially thought. It appears that there is a significant association among age and gender. Now, nothing in this problem said assume conditions, have been met. So here are the 3 conditions right here. Random, it was given in the problem. Random given. Okay. Each expected is at least 5. And the counted, oh, it's counted data, okay, not measured, okay? It is counted, all right? And that is chi-squared test of independence. Problem number 6 is a combined distribution problem. We did many of these. Sometimes we added the two distributions. In this particular one, we're going to subtract them because it's a comparative. It's a head-to-head competition of one versus the other. So I'm getting a little ahead of myself. The information is all about these two swimmers who are swimming the 100-meter backstroke. They have established enough times of doing this that we can see that their data is approximately normally distributed. Swimmer number 1 has an average of 76.76 seconds with a standard deviation of 3.08. Swimmer number 2 has an average of 77.9 seconds with a standard deviation of 2.49. And the first part of this problem, A, simply wanted to know what would be the combined distribution if we subtracted them. Okay. Well, all you do, like I said, sometimes you add, sometimes you subtract. On this particular problem, they told us to subtract. And the difference in the two means is negative 1.14. Now remember, this is time. So a negative means in any given race, swimmer number 1 is expected to be faster by 1.14 seconds. But then we need the standard deviation of that expectation. And the rule was it doesn't matter whether we add the two distributions together or subtract one from the other. When you combine the standard deviations, you always do it the same way. You square the first standard deviation to make it a variance. You square the second one the exact same way. You add them both together, and then you take the square root of them. So the combined standard deviation in this problem is 3.961. All right, now the next question is a very familiar question. Okay, using the results from part A. Okay. What is the probability that the second swimmer will beat the first swimmer on any given race? Well, remember what that negative 1.14 meant. It meant that in any given race, the first swimmer is expected to be faster by 1.14 seconds. So where does swimmer number 2 start beating swimmer number 1? Okay, well, they tie at 0. So 0 is the mark of just an absolute tie. And anything to the right is where swimmer number 2 starts winning. Because anything to the left is swimmer number 1 is still winning. Okay, his expected win is by 1.14 seconds. But anything to the left of 0 says swimmer number 1 is winning. Okay, anything to the right is where swimmer number 2 wins. So we're going to find the z-score. 0 minus negative 1.14 divided by 3.961. Okay, and remember this again is a z-score. It's not the answer. So look up 0.29 on your z-chart, but we shaded to the right. So 1 minus 0.6141 is 0.3859. Okay, and the problem said round it to the tenths. No, it said round to the hundredths. So 0.39. Now the interpretation of that is for any given race, the probability of number 2 being faster is 0.39. The problem didn't ask for that, and you wouldn't have had to have done it, but I just wanted to put the answer in context, because now you're going to use that for help in the C part of the problem. The C part of the problem says, okay, the two swimmers race against each other in 10 races. What's the probability that swimmer number 2 beats swimmer number 1 in 6 or more of the independent races? Okay. So this turns into a binomial CDF problem because 6 or more means 6, 7, 8, 9, 10. Okay. And we're going to use the calculator, and look what they did in the B part of the problem. They set you up perfectly for doing this. Okay. In the B part of the problem, we established that swimmer number 2 has a 0.39 chance, okay, of winning any given race. So what's the chance that swimmer number 2, okay, is faster than swimmer number 1 in 6, 7, 8, 9, or 10 races? Okay. So it's a binomial CDF. Okay. Although we're going to the right, okay, our calculators don't go to the right, they go to the left. So if we want 6 or more, we ask our calculators for 5 or less, and then we subtract that answer from 1. Okay. So I just did it all at once. This is what I would do in my calculator. 1 minus binomial CDF, 10, 0.39, 5. I added this problem to the packet because I looked at, I was looking through all my practice problems, and I thought, I don't know if we have practiced this concept yet. I know we've done it, okay, but I don't know if we have recently practiced it in any of the previous packets. So I threw this one in. Okay. The whole idea of the problem is, do golfers play better in the first round of a tournament, okay, versus the fourth round, which is the last round? Okay. So you figure golf tournaments go Thursday, Friday, Saturday, and Sunday. Okay. The first round is Thursday, Sunday is the last round. Okay. Do golfers play better in the first round? Okay. That's the question. So they randomly selected, I think 9, yeah. Yep, n equals 9. They randomly selected 9 golfers from the British Open. Okay. And they recorded what they got in the first round and what they got in the last round. Okay. Here was the data for the first round. Here was the data for the last round. Okay. And here's the data for the differences, as defined as last minus first. So if you take the last minus the first, here's the difference. Now this is going to be one of those ones where if you had this on the AP test, they would not expect you to put this data in the calculator. They would give you summary data. Okay. So as far as the first round is concerned, here's the mean and the standard deviation. As far as the last round is concerned, here's the mean and the standard deviation. As far as the differences are concerned, here's the mean and the standard deviation. So they're not giving anything away, because they're giving you more information than you actually need. So perform the appropriate test to investigate if players play better in the first round. Remember, in golf, the lower score is the better score. Assume all conditions are met. So the first thing that's being asked is, hey, what analysis are you going to do? And this is definitely a matched pairs test, okay? Because these two scores are from the same golfer, and these two are from the same golfer, and these two are from the same golfer. So it's definitely a matched pairs test, which means we are not going to need the data from the first round or the last round. What we need is the difference data. So, like I said, I don't remember having done this, So I wanted to make sure that we reviewed how to do a matched pairs t-test. Okay? Because the HO and the HAs are a little bit unique. The HO, the mu of D, okay, the average difference equals 0. Okay? Now, the HA in this case, the average difference is greater than 0. Okay? And the reason it's greater than 0 is because we expect, if we go last round minus first round, okay, we expect the last round to be a bigger number than the first round if, in fact, golfers play better in the first round. Okay? So we're really testing to see if mu of D is greater than 0. If you notice, most of these numbers are positive, a few of them are negative, but most of them are positive. Now, define the D. D equals last minus first. Okay, so a higher number minus a lower number is expected to be a positive number, and that's why that's the alternative hypothesis. Okay. 8 degrees of freedom. Okay. So the critical point on the T-chart is 1.86. Okay. The calculator tells us this is a regular t-test. Nowhere on your calculator are you, when you do stat test, nowhere are you going to find matched pairs t-test. It's just a regular test. Okay? With a null hypothesis of 0. It's a one-sided high test. Here's what you put in for the X bar. Here's what you put in for the standard deviation. And you get a t-star of 1.45. Okay. That's not in the rejection area. Your calculator will also tell you that the p-value is 0.093, which is greater than 0.05. So any way you look at it, this is a fail to reject HO. So at 95% confidence, there is evidence to fail to reject HO. Golfers do not seem to play significantly better in the first round of a tournament.